I'm your host, Grayson Brulte. Welcome to another episode of SAE Tomorrow Today, a show about emerging technology and trends in mobility with leaders and innovators to make it all happen. On today's episode, we're absolutely honored to be joined by Dr. Michael Harenbrock, Principal Expert Electric Mobility, MANN+HUMMEL. On today's episode, we'll discuss the new SAE J3325 Battery Pack Venting Safety Technical Report, a game changer that makes electric vehicle batteries safer than ever. Before we kick off the conversation, a quick word from Dante with the SAE Standards team.
Hello, everyone. My name is Dante Rahdar. I'm the Ground Vehicle Committee Manager for SAE. I want to talk to you all today about volunteering to join an SAE committee. SAE is an unbiased neutral convener. We want to bring together as many different people as possible to build out the best documents that we can. Our committees are composed of students, subject matter experts within the field, recent retirees. We're willing to take as many experts as we can to build the best documents that we can to help the industry at large, tackling really diverse subjects such as AI, V2X, electrification, fuel systems, truck and bus, all that. So you can go to sae.org/participate to go to the overview page on how to join one of our committees. We need as many hands on deck as we can.
Michael, welcome to the podcast.
Thank you very much, Grayson. Thanks for having me.
It's great to have you here. There's a lot changing in electrification, and there are some consumers that see a news, I can't buy an electric vehicle because it might catch on fire, or I saw this on the news, or I saw that on the news. And there's a lot of misinformation and a lot of concerns. Overall, do you think globally consumers trust that their batteries in electric vehicles are safe?
I would say so. At the end of the day, sales volumes of electric vehicles are steadily increasing, especially also in China nowadays. We have regional trends. There's investigations from insurance companies which compare the likelihood of a vehicle to catch fire. And what they found out is that battery electric vehicles are even less prone to fires than vehicles with internal combustion engines. And so at the end of the day, the vehicles are already pretty safe. But, you never know what happens. So you could have some extreme conditions like flooding events, something like that, which could also lead to battery fires. And of course, if severe events happen, that can really give a bad name to the whole industry. And that's why we all should strive for making it even more safer. And that's also what current and upcoming regulations on battery safety really mandate.
To me, it's that once an individual drives an electric vehicle and lives with it, you can't go back. I'm on my second EV. I can't go back. It's the convenience and it's heavier. You feel because you feel you're hugging the ground better. It just seems that to get over that hump of individuals drive and live with it, that though those fears tend to go away. But I think which is really neat. What you're working on is battery pack vents. That was fascinating. From a safety perspective, where do those come into the picture? What do they do?
Yeah. If we talk about battery safety, we always have to see that we have so-called holistic battery safety management systems. So it starts with the battery cell to make sure that the cell is okay, no production items whatsoever, and ends up with the vehicle integration. And so battery pack vents are somewhere in between battery cells and the vehicle. So they help the battery pack to fulfill its task. And those vents often have two functions. On one hand, they enable pressure equalization between the battery pack interior and the ambient atmosphere. And on the other hand, they enable the fast relief of overpressure caused by vent gases, which are created by battery cells if they run into malfunction, something called some runaway event, for example. And here, that's really a very important function those units can also do.
How do the vents function? Are they on the sides of the vehicles, the back of the vehicle, in addition to a tailpipe, or where do the vents push out those gases?
Yeah, so there's really no, mandate where to place it. So normally, what I'm in favor of is to place it on battery walls, so the vertical ones, because if you put it on the top of the battery pack, you could run the risk that vent gases are guided towards the passenger compartment and the cabin. And so this would mean that we have a higher risk of vent gases getting into the cabin. And those gases can be toxic, they can be harmful. And so this is something to be avoided. So my personal preference is to put it on a vertical battery wall facing towards the rear section, where you would have the exhaust pipe in regular vehicles with internal combustion engines.
You're the chair of the SAE Battery Pack Venting Committee. You're working on the SAE J3325 Technical Information Report. Is that an example, something that the group is working on, of, if you want to call it, a best practice of where those gases should exit?
Yeah, absolutely. But before I go more into that, just wanted to thank, on one hand, SAE and also the committee members to make me chair. It was really an excellent experience, great teamwork. And I really loved to lead the activity leading to this information report. So I think that there's a common understanding that that would be a good solution. But at the end of the day, it really depends on the actual pack design, where those vents have to be placed. You can have several vents also placed, let's say, in the longitudinal walls, but then you would still have to have some guidance how they exit, the gases exit the vehicle structure, so the chassis in general. And that is something that's very much depending on the actual pack and then also vehicle design. So this also plays a role.
How much does battery pack design vary? Does it vary by manufacturer? Does it by the design of the vehicle? How much variation is there?
It's getting very, very complex. So when I started to work on those topics like 15 years ago, there was a very clear way how to build your battery pack. So you had your battery cells, you put them into modules, and the modules were then assembled to make up the battery pack. But now we want to put as much battery cells into the pack as possible, especially with lower cost, lower energy density cells like LFP. This means you put as much in as possible, and so you more or less remove the module level. So you just have a pack, you maybe have something like a truck or something like that, and you put as much cells in as possible. So that's called cell to pack or cell to body, cell to chassis, you name it. But then there's also additional requirements where you see if you have your pack really as a kind of structural component, you also have to have some longitudinal and cross struts to give it more stability, especially in crash situations. And so you form more or less compartment for the cells. So you can see it's getting very, very diverse. And of course, those diverse battery packs also have different requirements. On one hand, on pressure equalization, but definitely also for emergency degassing.
The cell pack, you're increasing the density. Does that raise the demand for greater ventilation there?
Let's take the two functions separately. So for the, let's say, pressure equalization, if you put as much cells into your pack as possible, you have very little free air volume in your pack left. And so this is more or less proportional to the need for pressure equalization. So the more free air volume you have in your pack, the more you have to take care of your pressure balancing. And so this means with those modern pack designs, the requirements might even get less. But if we take a look at some runaway conditions, we have more energy packed into our system. And so we have to make sure that we have enough space and area available to get the vent gases out of the pack. And especially high energy chemistries we see nowadays with high nickel content, something like that, really need more than one of those venting units. You could have 2, 4, 6. I've seen systems with 8 of those units just to get all the gas out of the pack as fast as possible for those higher energy cell chemistries.
Then I'm going to take us one step further, because if there's a trend in China where battery swapping is becoming a very large trend, does vent design have to change if you're putting into a vehicle that incorporates battery swapping?
I think that is not a big factor which is influencing the design and choice of venting units. I think the charging could even be more smooth if we do it with battery swapping, because they take the battery pack out and then they would not charge it at highest charging rate, because it's not like somebody is waiting for exactly that pack. And so you might even do it with less stress on the battery pack, which might even increase the lifetime of such a pack. But of course, as it's swapped and used as often as possible, the overall lifetime of a swappable pack might be reduced compared to regular use. Normally you may have 5% of the whole time that you would operate such a vehicle. So most of the time your vehicle would be standing somewhere. But if you do the battery swapping, of course, they want to reuse the pack as often as possible.
Is it the stress which causes the gases to exit the battery, or what's causing that?
Yeah, so there's different so-called failure modes, which could lead to the gas release. So on one hand, we have mechanical damages. So that's, let's say, in crash situations, for example. What's especially critical is overcharging. So if you have, let's say, a failure in your battery management system, you just continue to put more and more and more and more energy into your cell until it really gets hot and goes into some runaway. Overheating is definitely also an issue. And internal shortcuts. So, for example, if your battery cell quality is not 100% okay, you might have some particles in there from the production process, which of course shouldn't happen. But, it's just Murphy's Law. It will happen if it can happen. Then this creates an internal short, which can also lead to some runaway event. And in this core, we would have first liquid electrolyte, which is being evaporated. And so, so there's different ways how to get into this gas release, and we have to take care of all the different potential failure modes to make sure that the likelihood of this to happen is minimized.
And then what happens when we go to higher volts of charging? Right now, there's a consensus. Porsche's working on this very publicly for 800 volt charging, because that seems like it would add more stress to the battery.
Absolutely. So here we have to make sure that the anode and cathode materials are compatible with that. Nowadays, now we have the Shanghai Auto Show. A lot of the large OEMs Chinese OEMs have announced chargers with 1.2 megawatt, 1.5 megawatt. And so I think the big challenge here is on the thermal management system of the battery pack. So if you put a lot of energy into the cell at high speed, this is not as effective as slower charging. So we create more resistance, we create more heat, and this heat needs to be dissipated. So we see that all the new battery packs, which are meant also for higher charging rates, also have more sophisticated thermal management system to dissipate the heat which is created.
When the team that you chair, the SAE Battery Pack Venting Committee, when the team came together, are you looking at every new emerging trend in electrification and battery technology and looking to incorporate that into the technical information report that you're developing?
That's a very good question. So in fact, we had our kickoff meeting and we sat together and we did a mind map. And this mind map clearly showed what we wanted to do and what we thought would not fit into the report. Because if you want to do the perfect report, which contains everything, you will never be finished. And so we said speed is of essence here, and so let's limit. So, but what was important to us is not only show how you can design venting units, but also where the functional requirements come from. So what's the basics, the physical basics behind the need for pressure equalization? What are the edge cases, for example, and also some runway. So we included that. And as I mentioned, we see venting units as one component in a holistic battery pack safety concept. And so we also had some information about adjacencies. So for example, what else can you do to reduce the likelihood of thermal propagation? What can you do to reduce the likelihood of battery fires, for example? And so we have information on this also inside the pack, because when you design the vent, you have to understand what other options you have. And then you just select the right solution for your pack design. Because else you optimize maybe one component, but you miss the overall optimum for the system because you've just looked at one component.
You're right. You have to look at holistically. When you look at reducing battery fires, did you get input from first responders or firefighters that have dealt with trying to put out these fires? I believe it's foam retardant that they're using today.
Not in that group, but a lot of the team members are also part of the SAE first and second responders task force. And so there we definitely talk about what can be done to extinguish the fires, what are good strategies. So we have something about fire suppression in. And one member of a research institute in Norway, they are very specialized in battery fires and what you can do about that. And so we have his contribution definitely also in the report. So it was really a kind of along the whole value chain. So we had something for academia, test labs, material suppliers, vent manufacturers, up to OEMs. So really covering the whole value chain to make it, let's say, reasonable and create value to the reader.
It goes back to what you said earlier. You're taking a holistic approach from different disciplines, different backgrounds, and you put it all together. You come out with this technical information report. What are you trying to accomplish with that report? What was the goal that you set out to accomplish when you started that? At
the end of the day, it gets more complicated and complex to select the right solution. And what we really wanted to do is to provide state-of-the-art information on where the industry is standing at the moment, the trends we are seeing, where the requirements come from, and to enable battery pack engineers working on the safety of the pack to take informed choices, to make selections, to broaden more or less the range of potential solutions he can pick from. And that's really what we wanted to do.
When it goes into practice and engineers start developing around it, do you see an increase in safety, an increase in reliability, an increase in potentially performance as well?
Yeah, absolutely. And apart from that, compliance with upcoming battery safety regulations is very much in the center. We've seen this trend driven out of China. They had the first regulation called GB 38 or 31 in 2020, which made very strong requirements also on how to prevent battery fires, and that you have at least 5 minutes to safely exit the car before any visible fire can occur, and also no toxic gases in the cabin. In the next round, it will be more or less no battery fire anymore. So no flame out requirements. That's something which has just been published and will become effective in 2026. And I'm very sure that this will drive additional steps for innovation on venting units, because we would have to see where can venting units contribute to comply with those new requirements.
That's fascinating. So you have no fire, which is great, because then I can also make an argument for different types of housing. So you're developing the venting units. Are they going to take different sizes, different design? And then when you throw in different battery chemistries, will that take a different venting unit as well?
Not necessarily different venting units. But you would have maybe different sizes. So the size of a venting unit, and if you need multiple or only one, really depends on how much gas is released by one cell. Then if it's only one cell which goes into some runaway, or if we have some propagation, and then also how fast this gas is released. So we have some chemistries like LFP, so the iron phosphate, which has been more or less reintroduced into battery packs, also driven from out of China. It creates similar amounts of gas like other cell chemistries, but over minutes, so longer period of time. So the gas release rate is much lower. Whereas if we talk about high energy NMC cells, for example, we create maybe 100 liter of gas just in a few seconds. And so this means for those chemistries, you have to have much more area available the gas can get out of the battery pack. And so in a nutshell, it's really not necessarily you have different designs, but probably different sizes and also different number of venting units.
And how do you deal with the pressure buildup that can deform the battery pack housing, and the seals can then dissipate?
Yeah. So that's more or less the question about the pressure equalization. So, if we had a hermetically sealed battery pack, so no ways of pressure equalization, and we would have different pressures inside and outside of the pack. So this can, for example, happen if you do a air transport of a battery pack, or if you're driving uphill, downhill, if you're driving through a tunnel whatsoever. Then you would have resulting forces which would start to act on the battery housing walls, and that could lead to deformation. And if you do that repeatedly, this mechanical stress can then lead to even cracks in the battery housing material, or you might have reduced forces acting on the ceilings. And then you could have contamination getting into the pack. And that's not a problem if you use 1 centimeter thick steel walls for your battery pack housing, but you cannot do that. So everybody wants to do lightweight materials. So we see materials which are lightweight by nature, and then also with thinner battery walls. This means that their stiffness and strength might be reduced to what we had in the past. And this means that this pressure balancing, so the equalization, so to prevent those kind of pressure differences to build up, needs to be taken care of. And that's more or less what the function is here. And with the trend to lightweight design, this definitely also becomes important.
When the pressure hits a certain point, is there an emergency switch that automatically kicks on to allow that pressure to get out?
So normally that's in the design of the venting unit itself. So it's normally not like you have something like electronic management system. It gets a sensor signal and then it acts. It's more or less integrated into the design. So for example, if we do some emergency degassing with a solution where we have a semi-permeable membrane, which is doing the pressure balancing, it can also act as a burst disc. And so if you exceed a certain overpressure inside the pack, this membrane is then pushed towards a spike or rupture device in the base plate, and then it ruptures. And then you can more or less play with that. So the membrane thickness, distance of the membrane to this rupture device, that more or less defines the trigger overpressure at which the membrane will rupture, and then the gas can get out of the battery pack.
What happens if there's an issue with the housing components? There's a crack or deformation or something happens? What happens then?
If you have a crack, the interior of the battery packs or the battery cells and electronics have to be protected against contamination by particles and also liquids, water, for example. So that's normally proven by fulfilling requirements of so-called international protection classes. So that's an ISO standard, which is giving the details here, called ISO 20643. This makes sure that even under, let's say, steam jet cleaning or submersion conditions, no water can get into the battery pack. But imagine if the sealing is not longer okay or you have a crack, then you could have an ingress of particles or even liquids. And that, of course, can lead to shorts in the battery pack and catastrophic events.
You mentioned lightweight materials, and there's all sorts of different materials. I'm curious, from a testing standpoint, do these go through rigorous testings when you're putting different materials there? Because you mentioned earlier, thick steel to light material. Okay, there's quite a bit of a difference there. Yeah. So, but that's a very good question. So what's well established in the industry for plastic materials is flammability tests. So there's some UL standards on that. But just recently, there's also been new test procedures released by UL, which test the resistance of plastic materials against some runaway events. So what you do is you have a box, you put in some battery cells, you have a test specimen on top, and then you just bring this one cell into some runaway, and then you have all the ejector particles, hot gases acting on a plastic specimen on top, and then you have some pass and fail criteria. So that's, I think, a very interesting next step forward, especially if we want to qualify new plastic materials. Is there a certain direction that the gas must flow when it's coming out of the vent?
So in the past, we have to differentiate a little bit between the different cell form factors. So for cylindrical and prismatic cells, they often have the cell vents on top of the cell. And so the vent gases and particles go straight up. And then you would have some guides which would lead the gases towards the exit port venting units on battery pack level. For so-called pouch cells, you don't have those designated directions, so they can more or less arbitrarily open, and so you would have less control over the vent path. But the latest development now is to change that. Because if you have the cell vent on top of your cell, the vent gas goes to the bus bars. And so you directly go into the high voltage components. The particles will just remove all the protection coating, and then you get an electric arcing, which is extremely dangerous and also can lead to fires and explosions. And so now we have more the trend to place the cell vent on the bottom, because then it's away from the high voltage components, which are on top. And then you can have proper vent guides on the bottom, maybe even over cold plates, to also take some heat out of the vent gases, which reduces the likelihood of auto-ignition of those gases. And so we definitely see some trends starting on battery cell design, which are then also taken up in pack design and there the venting units again can play their role. Like I mentioned, it's holistic, right?
And it is. And eventually, will those trends work its way into the information report? Will you update that over time as new technologies and trends enter the market?
Would have been great if we really could have a very, very broad scope. But what we ended up with is, on battery cell chemistry level, we have lithium-ion battery cells with liquid electrolyte and typical automotive operating conditions. But, a lot of the findings can also be applied to other applications. What I'm really looking forward to is what happens with new battery cell chemistries. So there's a lot of discussion about sodium-ion battery cells, for example, and solid state. And so I think there's still a lot of work to do, but this is also where SAE has some committees on. And so I'm joining those committees too to understand what's the latest and greatest and see when the technology and the knowledge is mature enough to place in such a kind of technical information report. Because, just because somebody publishes a result doesn't really mean that it should appear in such a technical information report. So we have to consolidate and the technology has to mature. But then definitely we will update that and edit.
Well, Michael, one thing's very clear. You're rolling up your sleeves, you're getting involved, and you're making a difference, and you have a very holistic understanding of battery pack venting. In your opinion, sir, what is the future of battery pack venting?
Yeah, so I think really to comply on one hand with the new battery cell chemistries we are seeing and the new regulations, safety regulations I was already hinting at. Sometimes I feel that there's not a very good understanding about what kind of safety measures you would need for a sodium-ion or solid-state battery pack. Because, for example, for sodium solid-state, the manufacturers or developers of those cell chemistries say, hey, this is safe. So we do the tests, everything's fine. With the idea, so you can take out some safety measures because the cells will be more expensive. I think there's no doubt about that. But you want to compensate that somehow with cost reduction on pack level. But, the failure modes of those cells can be different from what we know from lithium-ion cells. So if you just qualify such cells on what has been established for another kind of cell chemistry, you might just miss something. So I'm not saying, hey, it's dangerous, keep your fingers from that. I just say, show me the evidence and just make sure that you have also found out if you have seen all the failure modes and you have worked against that. Because from my perspective, what can burn will burn. And so it's just a matter of statistics. And all we can do is to reduce the likelihood of those events to take place. And when they take place, to reduce the negative impacts that those events have. So this is really one topic. And the other is really to see what we can do with regard to the upcoming regulations. So here, I think topics like integration of spark arresters is interesting. So they hold back particles which are emitted from the battery pack. So the larger ones can ignite gas mixtures outside of the battery pack. So that's battery fire relevant. But also smaller particles can be pretty harmful. So I would not say maybe toxic, but it's harmful to first and second responders. And to see if we can also keep those particles from getting out, contaminating also the environment, that would be good. And then the other topic is to take a look at early warning. So, you want to have as much time as possible after the first failure happens in your battery cell to safely leave your car, to have, let's say, safety for the first and second responders. And so we are also envisioning to take a look at integration of sensors onto venting units, which can help as part of a holistic sensor fusion concept to detect thermal runaway very early. And so also to contribute to this safety regulations.
I would summarize it this way, Michael. What you and the committee are building, you're building trust with consumers when they purchase an electric vehicle or they rent one or they ride in one. They trust that the incidents that they've seen in the past are not going to happen again because the breakthroughs in battery pack venting technology. Michael, as we look to wrap up this insightful conversation today, what would you like our listeners to take away with them?
The industry is doing everything to make the safe electric vehicles even more safer. But to really do that, and especially also with the need to fulfill new requirements, also cost down requirements, for example, I think it's very important to collaborate along the whole value chain, like we did in our committee, from academia up to OEMs, and really to understand what are the new challenges which are upcoming, caused by battery pack design, cell chemistries, regulations, you name it, and how this can really even grow further. Like I mentioned, so if you have one or two very negative events, this can really give a very bad name to the whole technology. And I think we shouldn't be afraid of the changes which are upcoming. It's just like make sure that we really investigate and that our statements are true and best to our knowledge, and that we don't rush those topics. That's what I would like to the listeners to take with them. And of course, those venting units are small components, but still they play an important role. So don't forget about them.
I like that. Don't forget about them. If you want to read the paper or read about battery venting, I think it's personally interesting. And I'll leave the audience with this. Electric vehicles are safe, and they're a lot of fun to drive. Today is tomorrow. Tomorrow is today. The future is battery pack venting. Michael, thank you so much for coming on SAE Tomorrow Today.
Yeah, thank you very much. It was a pleasure.
Thank you for listening to SAE Tomorrow Today. Be sure to join us next week as we explore Maine Mobility's latest driver app deployment and how adaptive AI and connected infrastructure power autonomous vehicle rides.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.